Compounds that contain carbonyl compounds, carbonyl functional group, all in one molecule, like as in this example, will do an intramolecular aldol reaction. So this is an example of 1, 2, 3, 4, 5, 6, 7 carbon. One has an aldehyde and the other is a ketone. And when you're considering where to start in an intramolecular, so you're doing the same reaction that you've seen before, in which one of the carbonyl is going to serve as an enolate and the other is going to serve as an electrophile. So one of the things to consider is which proton to deprotonate, right? So you have alpha proton here that's drawn here, and we have another alpha proton there, and then this carbonyl also has an alpha proton there in reacting with this carbonyl. Now in this example we have an aldehyde and a ketone, and as you know from unit 2, which of the two is better at serving as an electrophile? Which was more reactive towards nucleophile, the aldehyde or ketone? You know that aldehyde is more reactive because it's sterically less hindered, and you have less electron density contributing toward this carbonyl, so this carbon is more electrophilic. So this is probably going to serve as my electrophile, and which means that I have choice between do I deprotonate here or do I deprotonate here. Now if I deprotonate here and put the negative charge at this alpha carbon, then this will go and attack the C-O, and the thing that you need to consider is what size ring am I going to make when I do that. So this will make bond between this carbon and this carbon. That will be 1, 2, 3, 4, 5 member ring. Whereas if I made a negative charge here in making the enolate here, then it would be 1, 2, 3, 4, 5, 6, 7 member ring. And as you know from 114, 5 and 6 member rings are the more readily formed ring size for many reasons, and 7 member ring is going to be harder to form. All right, so that's why we're going to make an enolate at this carbon, attack it, and open up the double bond. And you're now draw a bond between this, and when you're initially doing it, by the way, don't worry about having a 5 member ring that's really pretty. I would just draw a line and then redraw it to make it look like a cyclopentane. All right. So once that carbon bond is formed, you have a negative charge at this oxygen, which is going to go and grab a proton to form this aldol product, addition product. And the if you allow this reaction to go further by heating it, then this will dehydrate. That's what is shown here, and the alpha beta unsaturated carbonyl product will be the final product. All right. So see if on your own you could do this reaction. This is an intramolecular reaction, so you have a carbonyl, and then you have the aldehyde, and so it's actually the same compound as this, but I want you to see if you could draw all possible products that can form, not just the major product that will form, which is this, but see if you could draw, for example, the 7 member ring aldol product, and also see if you could figure out what the product would look like if the enolate did form here and then reacted at this carbonyl. What would that ring look like? All right. So once you do that and then do 22.25, I want you to then come back to this and see if you could do synthesis using Aldol reactions, which is what I'm going to go over next. All right. So in doing synthesis, one of the first things that you have to do is be able to recognize the functional group and ask yourself what reaction would I use to form these products. So in using Aldol, the functional group that you're looking for to be able to do Aldol is the beta hydroxy carbonyl. So that functional group there. So anytime you see this in your product, think Aldol. Now, one step further than that, because you know this could easily dehydrate, the other functional group that you're going to be looking for is the alpha beta unsaturated carbonyl. In other words, some kind of alpha beta, so some kind of functional group that looks like this. If that's present, then you should think Aldol. All right. So let's begin with what if beta hydroxycarbonyl is the product that you needed to make? Then how would you go about doing synthesis problems? All right. So when you see this beta hydroxycarbonyl and you know that this product came from Aldol, you know that one part has to be the nucleophile enolate. So we know that the electrophile is some kind of unreacted carbonyl, and then the nucleophile is some kind of enolate, right? So those are the things that should be going through your head. And when you look at the product, you have to then ask yourself which part was the nucleophile and which part was the electrophile, and specifically which carbon-carbon bond was made. So what two things came together to make this product? Okay, so this carbon and this carbon, that's where the carbon-carbon bond formation took place. And the part that served as the nucleophile enolate has to be the one that still has the carbonyl. So this must have been the enolate, and then it must have reacted with this part of the compound, in which this was the OH comes from the aldehyde or ketone that didn't react, right? So this used to be the carbonyl, and in this case is a benzaldehyde. So basically we're dissecting it backwards, in which we're trying to figure out what enolate was used and what aldehyde or ketone served as an electrophile. So this is my electrophile, this is my nucleophile, right? So going forward, notice that if this reacts that this carbonyl, then it will form that bond, and you're basically done at that point. All right. Now you have to also show how this was formed. So you have to show how this nucleophile was made. So you would start with a ketone in this case, and the question now is what kind of base would you use to form this particular enolate and not the enolate over on the other side? Because notice this is a unsymmetrical ketone, so I have two different kinds of alpha protons. I can remove the alpha proton here or alpha proton here, and notice that this is the enolate that I want to make is a kinetic enolate, because I want to remove a hydrogen from the less substituted carbon, so that the enolate is less substituted. So probably the best base to use this is an LDA, and that would depronate definitely this proton, because remember this is a strong base that's very, very bulky, so it's going to grab that proton, and then you throw in this aldehyde, and then you will get that product. All right, and in a multi-step synthesis, it's possible that you have to keep going back, and then you would ask yourself how you would make this and keep going back. But I just want to focus on being able to use aldol to do the synthesis problems. All right. And then for alpha beta unsaturated carbonyls is a one step more than that, because we know that the alpha beta unsaturated carbonyl comes from the dehydration, right? So if we remove water by heating from a beta hydroxy, so this is alpha, this is beta. So if I had this precursor in which I removed H and OH as water, then I will be able to form the conjugated enone. That's another word for this alpha beta unsaturated. So all I would require to do is, if I have this, I would just heat it to get that. And then here is a same problem as what we had over here. So once again, I asked myself which carbon-carbon bond was formed in this beta hydroxy carbonyl. It was the alpha and the beta, this bond that was formed. Which part has the carbonyl still? So this one. So that must have served as my enolate. And then this must have served as my electrophile, or the aldehyde in this case. And then, so then here, I need to show how I could make the this enolate. And once again, we could use LDA if you don't want self-condensation to occur, or because we're doing a reaction with no alpha hydrogen, it's possible to use a weaker base and then react with an aldehyde, but LDA is gonna definitely do the job of removing the alpha proton and forming the enolate, in which then you would throw in the electrophile, the benzaldehyde, and then come up with the beta hydroxy carbonyl, in which you heat it to remove to make the alpha beta unsaturated enone. All right, so that's how you would go about doing these synthesis problems. So I expect you to be able to, there's tons of problems that your book has for these synthesis. I expect you to be able to at least do couple, but I expect you to be able to do most of it, and then if there are issues or problems, to bring it into class, and then we'll go over it during class.